Hello, everyone. Good evening or good afternoon, wherever you may be joining us from. I'm delighted to extend a warm welcome to each and every one of you as we embark on this exciting webinar journey together. Today, we have the privilege of introducing two exceptional speakers. We have Mr. Abdelkader and Mr. Hamdi. Both are esteemed professionals from BlackBerry QNX, a pioneering organizational in the field of Unix-like operating systems. I would like to highlight that this webinar is part of a series of insightful sessions that we have been hosting, covering a wide range of topics such as software-defined vehicles, embedded Linux, and more. If you haven't had the opportunity to explore our previous webinars, you can access them conveniently from the dedicated YouTube channel, where you can find a playlist of automotive-related webinars. And as we gather today, let's embrace the spirit of learning, collaboration, and innovation. We invite you to engage actively, ask questions, and make the most of this valuable opportunity to meet the experts. Without fear, Ado, I hand over the virtual podium to Mr. Abdelkader and Mr. Hamdi, who will lighten us with their expertise and reach on understanding of the fascinating world of the Unix-like operating system. Once again, welcome to this enlightening webinar, and thanks for joining us.
Thanks for the introduction. Can you just confirm that you can see my screen?
Yes, it's being shared.
It's coming, yeah. Yeah, we can see it now.
Okay, great. Okay, I'll get started then. So the agenda for today, we're going to start off by giving an introduction of BlackBerry QNX, where it is as part of BlackBerry, what business are we in, some of the customers that we work with. And then we're going to go into an overview of the microkernel architecture, what makes it different than other architectures out there for operating systems. And then we're going to switch focus to the QNX OS, so our microkernel that we developed here at QNX, and what makes it different than our competitors and other market solutions out there, give an overview on that. And then we're going to go into solutions, QNX solutions for software-defined vehicles. We're going to go through some use cases, market trends of what's driving the next wave of innovation in the software-defined world, whether it's vehicles or elsewhere. Talk about a few solutions, really with an emphasis on the hypervisor, which is one of our core and very critical solutions that we have. And then at the end, we're going to wrap up. In the wrap-up, we're going to have a few links, including a link for evaluation licenses, and other links that you might find relevant, so you can go online and be able to access some of our products and try them out. Okay, so BlackBerry as a company, of course, historically they've been making phones, but in the last 10 years they have shifted focus to really two divisions. So there are two divisions in BlackBerry, one cybersecurity and one is called IoT, Internet of Things. QNX is really the centerpiece of the IoT division of BlackBerry. And really, if you look at some of the work that we've been doing and some of the products that we have, you look at the QNX, what we call this SDP, software-defined software development platform, BlackBerry Ivy, Certicom, Radar, they're all under the IoT umbrella. If you look at some of the key highlights that you see is we're approximately in 250,000 cars worldwide, and of course other millions of other systems in industrial, medical devices, robotics, commercial vehicles, and other areas. If you look at some of the customers that we work with, you will see a variety of customers worldwide, whether it's North America, Europe, Middle East, Asia Pacific. You will see a variety of customers on this list, and of course some partners, and for those in Egypt, Valeo is on the list, so we work very closely with Valeo. So really what QNX is known for is providing software solutions that are reliable, safe, secure, that are really meant for embedded systems. That's really our focus. We've had the trust of the market for over 40 years. We have the experience. We have the performance in all different types of markets. We have various services on top of the OS and engineering services to complement our core products. We have a big software ecosystem, whether it's through partners or, of course, open source ports that we have. And lastly, we have strategic partnerships to really enhance the ecosystem on top of QNX. So I mentioned safe, secure, and reliable. Really, when you look at some of the high-level requirements that you see in embedded systems, whether it's today or historically, real-time behavior is very important. And we're going to go into details on what is real-time, the different types of real-time behaviors out there. Highly performant. And when we're talking about performance, we're talking about various characteristics of performance. We're not just talking about throughput, like network throughput, like how much data can you stream through the network stack. No, we're talking about quick response from the kernel, startup speed, flexibility, and other features as well with regards to performance. Security is a key feature, so having a big variety of security features that are out there with the OS. Highly dependable, so that means that the OS doesn't crash. The OS, when I say doesn't crash, I'm talking about you can leave the OS running for tens of years with applications running on top, and you will never have any issue. Like the last thing you want when you're running a reliable safety critical system is to have, like, for example, the blue screen of death that you've seen in some of the OSs that you use, whether it's desktop or enterprise. Minimally offline, so that goes with dependability. Deterministic, and this goes to the real-time aspect. And of course, long-term support, so being able to support the OS and our customers on a specific product for 10 plus years, because depending on the industry that you're in, the life cycle aspect of a specific system can range from 5 years to 10 years, and some systems, the end of life is 20 to 30 years. And when you look at the industries that we're in at the bottom, you will understand why some are 5 years and why some are 30 years. Like if we look at heavy machinery, energy, so being part of the electrical or nuclear grid, aerospace and defense, those are aspects that those are systems where you can see the end of life for these systems really ranging between 10 to 30 years. Of course, when you look at IoT devices, maybe transportation and medical devices, the end of life for these devices can probably range between 5 to 10 years. Some aspects of medical can be a bit longer, like MRI machines, but depending on the end system that you use, the lifespan changes, and being able to support that is key. So the software development platform is really the cornerstone of all QNX products. The software development platform is called SDP, and it comes with different aspects of whether it's the OS, the tooling that comes with it, and a solution that manages installations, updates, licensing, all of that. So that's part of what SDP is. All the products that we release on top of it, whether we're talking about middleware, hypervisors, documentation, the training, the open source ports, the libraries that we provide, all of that is built on top of it. So when you get SDP and you're buying add-on products from QNX, they will all just work because everything is pre-built on that OS and on that platform. So if we look a little bit closer, SDP is composed of 3 components. So number one, and of course the primary aspect of it, is the QNX operating system. And then number 2 is the QNX tool suite. And then lastly, QNX Software Center. So when we look at the QNX OS, there are 3 aspects of it. So of course, what we call is the core OS, the core operating system, that comes with the microkernel, all the security feature, networking, utilities, whether it's for running utilities on the target or for debugging purposes, that's all available. Connectivity functionalities, file system, scheduling, audio, and many other functionalities that come as part of the OS. We also have what we call QNX Screen. So QNX Screen is really graphics. So we are providing all the functionalities that you need to support graphics, whether it's composition, codecs, fonts, video support, windowing, whether it's support for OpenGL, Vulkan SC, and other features and functionalities. And lastly, of course, hardware support. And the reason why it's broken up like this with regards to hardware is because what you see of our architecture, because we're a microkernel, the BSP and the drivers sit outside kernel space, so you can really put aside the hardware support as a separate line item. And we have support for different architectures right now. So ARM v7, ARM v8, x86-64, and of course, what's coming is ARM v9. And of course, RISC-V is also something that we're looking at as well. So we're looking at, when you look at hardware support, you have a variety of different architectures. And of course, that means different hardware, whether it's coming from the NVIDIA's, Qualcomm's, NXP's, TI, to the Intels of the world, right? So all of that is supported with QNX. When we look at the tool suite, so this is really when you're doing development, all the functionalities that you need to do development successfully. With QNX, you have two IDEs, so integrated development environments. Number one is our proprietary IDE, so that's what we call the QNX Momentix. So this is a custom Eclipse-based IDE that comes with all the tooling that you need for software development, management and debugging of the targets that you're using, and of course, all the customizations that we do to really manage QNX targets very effectively. We also have a toolkit for Microsoft Visual Studio Code, so VS Code. That's the name that's used in the market. So if you're used to using VS Code as a development environment, you can go on VS Code Marketplace and you can download an extension called the QNX Toolkit, and really it gives you all the functionalities that you would be getting with Momentix that is custom. So all the QNX customizations are part of it. And lastly, there are many developers who do development and debugging on command line. So providing a lot of command line tooling to be able to debug, analyze, profile your system effectively. So providing all the tooling with QNX is really key. So that's part of the tool suite as well. When we look at QNX Software Center, which is the last piece of the QNX Software Development Platform, SDP, there are two components of Software Center. One is the functionality that allows you to manage your installations, get all the updates, get all the notifications, and be able to have configuration management on the installations that you have. This is really essential, so you can have a central repository where you can manage all of that. And then the other aspect is license management, to be able to manage the licenses that you have, to ensure that you're compliant, whether with GPL licensing or QNX licensing. So all of the functionalities associated with license management is provided there. So now that we've covered SDP, I want to switch topics a little bit and talk about something called QNX Accelerate. So QNX Accelerate really is an initiative to try to reduce developer friction. We know that hardware nowadays is not just becoming expensive, but also it's becoming hard to come by. The chip shortage during COVID and until today has made it clear that trying to get hardware is becoming more and more challenging. So what we have been doing with some of our superscalers is deploying our OS in the cloud. And really the lead work that we've done is with AWS on Graviton 2 and Graviton 3. So if you go on AWS Marketplace, you will see our hypervisor, our OS available to run in the cloud. And really the reason why we're providing it is the cloud is an ARM-based architecture. It's based on an ARM-based SoC, Graviton. Obviously, Graviton 2 is ARM v8.0. Graviton 3 is ARM v8.4. Graviton 3 is ARM v8.4, and then Graviton 4, which is coming this year, is ARM v9. So by providing the OS to run on these different Graviton boards, it allows you to do a lot of the development, initial testing, early integration in the cloud without having to need a hardware, whether it's in the test lab or at your development environment, like at your cube or in your office, to be able to do some of the testing. And it makes it easy as well as if a test engineer runs into bugs or some issues when they're running the test, debugging that issue with a developer who wants to go in and access the system and reproducing it is very seamless in the cloud versus real hardware target. So the core benefits of having the OS and the hypervisor and other functionalities in the cloud is being able to scale a lot better from a customer standpoint. You want to be much more efficient to be able to have really CI/CD pipeline integration where you can run initial sanity testing, development, profiling, and other aspects in the cloud as quickly as possible. And of course, it makes collaboration a lot easier when you have an image that is easily accessible across the world. So what ends up happening is that if you're, let's say, in Cairo right now, and you're doing some development or some testing, and your customer or your team member in North America or in Europe wants to go in on the environment that you're using and see what's going on. If you're running into issues, they can do that a lot easier than if you're using a real target in the lab in Cairo. That's just an example. So when you're choosing an embedded an embedded software platform, there are really three aspects that you have to consider, right? So one thing is technology. Does the software platform that you're looking to select has the technology that you need? Whether we're talking about real-time behavior, specific features with networking, graphics, file systems, and other aspects associated with it, including hardware support. And of course, with the rise of artificial intelligence and machine learning, you want to be able to ensure that the software platform that you're using comes with all the functionalities that you need from day one to support the project or the product that you're trying to deliver. Secondly is the ecosystem. You want to ensure that if you're using specific partners or specific third-party software, libraries, utilities, those functionalities are available from day one to be able to use them on that platform that you're picking for embedded for an embedded project. So you can ensure that the ease of use from day one is a lot more seamless. And of course, future proofing. So how do you ensure that whether it's end of life support, CVE management, safety critical bugs, implementation, and roadmap updates that come with the OS, and having a plan for new hardware support with the OS or with the hypervisor or with other aspects of middleware is already available for 10 plus years. So those are the key aspects of really trying to pick and ensuring that you're picking the right software platform for embedded projects. Now, a question that I always get is, okay, QNX is closed source, it comes with licenses. What are the key differences between QNX and an OS, for example, an open source OS like Linux or FreeBSD or others out there? Putting aside the technical aspects of whether we're a monolithic versus like whether Linux is monolithic and what a microkernel, real-time versus non-real-time, I will put that aside for now. I want to focus on the business aspects and things that you should consider. Is one thing, first things first, it's commercial grade. We do all the testing as a proprietary OS. We do all the testing that you need to get an OS that is production and mission critical ready from day one. So you can use the OS for tens of years from day one and not have to run into any issues. The maintenance, the support, CVE bug fixes, and other updates that you might be interested in is managed by QNX. And of course, it means that because we manage all of that, we really have tailored development. So we work very closely with our customers across the world to ensure that we have the specific functionalities that they need for their use cases. Of course, we work with partners, ecosystem support as well to ensure that all the specific and key functionalities that is needed for their use cases is there. We don't provide generic functionality, we provide very tailored functionality. And when it comes to tailored development, it goes hand in hand with a specialized roadmap. So our roadmap is very tailored for the industries that we're in and the customers that we deal with. And then lastly, the safety certification. So safety certification is key, whether you're in automotive, industrial, medical, and providing a safety certified OS with all the safety artifacts. Same goes with the hypervisor, libraries, and other aspects is key. And this is really, when you look at it, the key differences, because when you go with an open source OS, you don't generally get all the testing and all the value add from being commercial grade, from going into production from day one. There is a lot of testing that you'd have to do to ensure that the use cases that you're using the OS for, when you get it from open source, is generally solid. Of course, you're getting more of a generic OS. There is a lot of features and a lot of functionalities from across the world being pumped into the OS if it's open source. So it becomes, okay, how do you cherry pick the features that you need? Because you don't want, I don't want to say that code, but you don't want features that are unneeded available and just sitting there but being used. And of course, with open source, you don't get safety certification. So there hasn't been an open source OS that has been safety certified. So what ends up happening is that if safety certification is key, you don't get with open source. So at the end of the day, with QNX, we expertly manage the OS from start to finish for the lifetime of your products and for your systems. We have systems until today that we support that are 20 years old. So just to give you an idea of the level of support that we provide. So I'll switch over to Ahmed to talk about the overview of the microkernel architecture and what makes it different.
Yeah, hello everyone. So thanks, Louay, and I will take over to speak about operating system. I think Louay spoke about the operating system in general and how would be the main functionality behind it. And here I would like to speak what is actually an operating system and what is the functionality behind that. So as you may know, most of you already in the different industries, I would say, the operating system is really the most important software which is running on any kind of computer. Computer, maybe a personal computer, maybe an embedded device, but really the operating system is playing the main role within your program somehow. Why is it? Because it's actually managing the memory, the different processes running on top, and everything related to software communication between the different processes integrated on this, and also the hardware with the underlying layer. It's always playing like the heart of all management between the different processes. And for sure, it also allows you to communicate to your hardware without really knowing the computer language and the underlying understanding of what the hardware will do with your commands to it. And the operating system in general is actually, it's a kernel. I think it's always here like, okay, now I will change the kernel. I have the kernel. So the kernel is really one of the main components which is forming an operating system. There is also a bunch of services around the operating system with the drivers, with this specific hardware, like networking, Wi-Fi, security features, file systems handling, graphics, and even much more. And this is just like the first basic understanding of what operating system means. Maybe we go to the next slide, which we discuss different examples of operating system architectures. I would say a very common architecture, which is well known in the market, is the microkernel architecture, which is one example is QNX. I will speak about that, and we will speak about that also with Louay later on. But the microkernel architecture is one example, which you have the minimum functionality of a kernel just put inside the kernel space, and most of the functionalities of the operating system services are put into the user space. I will come to that later, but just for a basic understanding, basic functionality of a microkernel would be virtual memory management, the scheduling, and inter-process communication. These are the minimum functionalities which you can put in a microkernel, and all other services, functions, other operating systems can give, you just put it outside the microkernel. And we put it in the user space. I will come to that in a few minutes. The second approach, which is also very common, and one example of that is Linux, for example, is a monolithic kernel, which somehow combines, or the kernel itself has the kernel functionality, but it also have a lot of the operating system services, part of the monolithic kernel. The drivers are part of the monolithic kernel. For sure, each approach or each design of these two operating system architectures have its own pros and cons. So one of them will give you more flexibility, granularity to change the different processes, switch them on, off, disable, enable, restart, shut down, whatever you need. And the other one will give you maybe the flexibility, maybe from processing time and accessibility of different resources compared to the other one. I will come to the comparison between both. There is another types which is not commonly used as of today. Most popular ones is the microkernel and the monolithic kernel. There is also the hybrid kernel and the nano kernel. So the hybrid kernel is actually a mixture between both. It's bigger than the microkernel. So the kernel itself contains additional processes also integrated into the kernel, but it's smaller than the monolithic kernel. For the nano kernel, it's something even more granular, even smaller than the microkernel, which give you more granularity and easier configurability of what you would like to do within the kernel, but it's also not commonly used like today. And I would say the most popular two as of today is the microkernel and the monolithic kernel. Taking two examples, QNX microkernel and Linux as a monolithic kernel. What is a kernel space and what is a user space? So kernel space is something running within the virtual memory space of the kernel. And the user space means anything running outside the kernel space. It's running in its own virtual memory space. And generally, the operating system uses the virtual memory to separate the address spaces between the user space and the kernel space. And this is one of the main advantages of the operating system to do this separation, because it gives us memory protection and hardware protection from any malicious or errant software behavior. Because if a certain process, a certain application running in a user space have the same memory space which is a kernel is somehow owning, it may actually damage the kernel functionality. And with this virtual memory separation, you always maintain or keep the application running in user space protected, or actually you keep the kernel protected from the application running on the kernel space. And that's actually the main advantage we will speak about in a few seconds when you go to a microkernel design. Because with the microkernel design, you have more granularity what is running within the kernel space and what's running into the user space. So if we take an example, as of today, I think a lot of people actually got used to Linux and other monolithic designs. A lot of operating services and the device drivers are part of the kernel, which means if you need to change, adapt, reconfigure a certain driver running within the monolithic kernel, or even switch it off, switch it on, or change it, you are impacting the kernel. But with the microkernel architecture, you can have everything running on the user space. You have your own applications. You have a bunch of operating system services. Yeah, we can talk about many services available on the operating system, like iNet, for example. Many services. We can speak about a lot of things here. I have a lot of in my mind now, but all of them are really running in the user space. And the most important one is really the board support package, which have all the hardware specific drivers. They're also separate, running in their own virtual memory space, and you can easily switch off any of them, you can update any of them, you can restart any of them without impacting the microkernel, without impacting the kernel itself. So just looking at this as an example, you have a certain functionality or certain driver, like maybe a serial driver. It's running in the board support package in its own virtual memory space. And at a certain point of time, you can just like restart this driver while you are not impacting the kernel itself. So it gives you the granularity to control the different processes without impacting the kernel itself. And this is a big advantage of the microkernel architecture. But being fair, is it really like the main advantage you get without any cons? That's incorrect. Definitely there is some cons for that, because the microkernel will play the role like, it will be like a bus master for all the communication between the different processes running in the user space. So if there is an application would like to have a specific operating system service or a specific access to a certain device, you have to go through the microkernel because it gives the inter-process communication functionality. So this causes a lot of context switching, let's say. So you definitely have context switching more compared to a monolithic kernel. Sorry. At the same time, you may also have more data copies because if you would like to transfer data between one application to another, you may also store it in different virtual memories to ensure that the data is transferred properly between the different virtual memories of process 1 and the process 2 through the kernel. And that's somehow the cons of using a microkernel. And at the end, it's a trade-off. So you have to decide which one is best for you. And here we try to list all the different attributes when we select a specific operating system design, which one is really I'm thinking about. So if we talk about the address space, so microkernel, as I just mentioned, it keeps the operating system kernel and services in a separate address spaces, which is different to the monolithic kernel because the monolithic kernel put both together under the same address space. The design, definitely, if you go with the microkernel architecture, you have to separate each process or each operating system services in its own process. So it may be a little bit complex from design perspective to consider all of these different aspects, while at the same time for the monolithic, because everything is just like put together from the operating system, kernel and services, then it's much easier in some situations from design point of view. From the footprint and the size, definitely the microkernel is much smaller, so it has a smaller footprint compared to the monolithic architecture. The functionality, the microkernel is more granular, so it gives you much easier possibilities to add new functionalities compared to the monolithic one. Failure of one component of the microkernel does not mean that the overall microkernel is impacted. You can just switch off this specific functionality or restart it. Compared to the monolithic architecture, if there is specific operating system service or a specific device driver may be impacting, it may lead to the complete monolithic kernel and failure for the entire system. Processing speed, microkernel is slower, as I just mentioned, due to this context switching and data copies may be needed. For monolithic, it's faster. Modularity, operating system, I would say operating system is much modular with microkernel. Monolithic is not modular. You need to customize their image. You need to build with the monolithic architecture to allow which services would be available for your image. But with the microkernel, it's already modular by design or by nature. Debugging, microkernel is pretty clear. It's easier to debug because most of the drivers are actually out of the kernel space. So you can easily see the processes and debug them. Difficult compared to how is it difficult actually with the monolithic kernel architecture. Maintenance and update, that's the last thing, which we also consider. It's always difficult to maintain and update the monolithic kernel because you need to rebuild the full image. But with the microkernel, it's easier because it's just like small set of functionality put inside the kernels, and then all the other processes, you can just keep them updated separately from the kernel itself. And that's somehow the design comparison we always talk to our customers about to select which architecture is better for you. And yeah, I think now we go to discuss about our particular QNX operating system microkernel, and I hand over back to Louay. He will speak about that.
Thanks, Ahmed. Okay, so the QNX OS at its heart, of course, it's a microkernel architecture. It's built with real-time behavior from day one, so it's a hard real-time OS. It was initially, the first release of it was back in the 1980s, and right now we have the 5th generation OS released with version 8.0. Of course, Ahmed spoke about the different features associated with the microkernel. When you look at mission-critical and safety-critical systems where real-time behavior, reliability, ease of updates, and modularity is important, the microkernel is a clear winner. And that's why QNX is being used in hundreds of millions of devices worldwide. Putting aside real-time aspects, the microkernel architecture is a key attribute associated with decisions that customers make. It means that it comes with real-time scheduling for CPU for the CPU and other resources, memory, drivers, and other aspects. And of course, it's compatible with standard tools, libraries, and frameworks that you generally are used in open source or from other popular software software makers out there like a Microsoft. The architecture that we've built with QNX incorporates security and safety in its design. We have a lot of security and safety features embedded in the OS that you can turn on and off and configure. You can sandbox specific functionalities and have them really isolated, update, have what we call a design safe state for certain functionalities. And of course, we've taken the OS and we've safety certified it to different standards. So automotive, medical, industrial, rail, all of that, the OS has been safety certified to the highest safety integrity levels. So at its core, and as a microkernel, we know that the QNX is a true kernel. Sometimes you see other other OSs out there in the market, whether open source or closed source. You see that really they call themselves a microkernel, but when you start asking what's running inside the kernel, you start seeing they're more of a hybrid kernel. They have more functionalities than you would expect from a microkernel. But really what we've designed is that inside kernel space, what we have and what the kernel is doing is thread management, so thread services, signal management, so signal services, message passing, synchronization, scheduling, timer, and process management. So, and of course, memory management. So all of that is being handled by the kernel. Everything else is sitting outside kernel space. So really what you see is that truly the QNX microkernel is a true kernel because we've limited the functionalities of what sits inside the kernel or inside kernel space to the fundamental and basic functionalities that you would see using that architecture. And of course, you see different aspects outside kernel space, like the file system, like you see on the slide here. On the software bus, you see the PowerSafe file system. You see the QNX Trusted Disk. You see applications. You see the message queue manager. So all of that is sitting outside kernel space, the networking stack, to really make the kernel truly a microkernel. So we mentioned real-time. Why is real-time behavior very important? When you have safety or mission-critical system, and of course in the image that you see here, you have a robotic arm running in a factory floor with a person, whether it's controlling it or maintaining it, being able to run consistently every day without failure, without having erratic behavior is key. You want to have predictability, determinism, and reliability. Because like if you, let's say for an example, you're manufacturing a medical device and you have a robotic arm that is somehow part of the manufacturing chain and a factory floor that's helping you build it. You don't want that robotic arm for some reason to misbehave, to have inaccurate execution, to have erratic behavior, to fail after a few hours, or to have bugs that make it stop. What will happen is you're either going to have a product that doesn't meet the standards that you would need, for example, for a medical device, or you could have the factory floor or that specific line on the factory floor shut down while you try to debug what's going on with the system. And that really puts into perspective the need for real-time behavior, because real-time behavior is pretty much ensuring that the system is predictable, deterministic, and reliable. It can run for tens of years without failing whenever you want low latency and low jitter, because when you're building something using a robotic arm or you're driving a car, for an example, you don't want inaccurate or imprecise behavior or responsiveness, because in some cases a 1 centimeter shift of a specific device that's using a real-time system can cause and can be catastrophic. Like if you look at, for example, in a surgical robot, let's say, for example, you're doing laser eye surgery and you have a laser being put in your eye and it's using probably a real-time system. And we are working with medical companies that do similar work. And what you see is that when you have something critical, a 1 centimeter, even a 1 millimeter shift in precision can be disastrous when you're doing something so highly accurate and precise with regards to its execution. So real-time comes in different types, right? You will see, for example, out there in the market, whether it's open source or closed source, different types of real-time OSs out there. But the question you have to ask yourself, what type of real-time is it? Because there are 3 types of real-time that's real-time behavior that's out there. There is hard real-time, there is firm real-time, and then there is soft real-time. So if we look at soft real-time, it really it's an OS with flexible constraints where the OS gives you a small window to run certain events, and it's usually not as precise. So there is more jitter, more latency, and if the execution that you're asking for to be executed in that specific time window doesn't actually happen, the system doesn't go into a fail-safe state, or it doesn't result in something very bad happening, right? So that's what soft real-time is that the way I look at it is when you soft real-time OS is an OS that says, I will do my best to try to meet your needs, but I'm not going to make any promises. A firm real-time OS is one that has fewer missed deadlines, but when there is a missed deadline, again, it will not lead to a total failure. So it has more strict time constraints, but you won't see it in systems where, for example, in a car or in a medical device, where if the system fails because of a missed deadline, it can end up in a disastrous situation. A hard real-time OS is an OS that not only, what I say, makes the promise, it fulfills the promise. So it has very strict time guarantees and time constraints, and very strict and guaranteed response times, because we know that missing a deadline is not an option, right? So having an OS with hard real-time capabilities means that when I want a thread to be executed within that specific time slice on a CPU core, it has to execute every single time you want that thread to run or other threads to run. It has to execute, and it cannot miss that deadline. It has to execute within that deadline every single time. Missing a deadline is not an option. So providing an OS with that type of capabilities, you can see where it would be used. Some of the functionalities that it would be used, like autonomous driving, like surgical robotics, and industrial machines or robotic arms. You can see it in railway systems where you have positive train control. Certain functionalities out there require hard real-time behavior, and this is where the QNX OS comes into play. Our design and our OS from day one has always been hard real-time. So Ahmed spoke about BSP development and how BSPs are easier with using a microkernel, and that is the case with the OS. One of the reasons why a lot of actually all our customers love us is because our architecture pretty much doesn't tie a vendor or a customer or an OEM or a manufacturer to a specific hardware platform, because the BSP sits outside kernel space. The board support package sits outside kernel space. Of course, there is variants of the OS for, let's say, for ARM and x86, because the instruction sets for each hardware architecture is different. But if you're, let's say, using ARM v8 and you want to go from one chip to another chip, really all you have to do is just update the BSP, right, which sits outside kernel space, and everything will run. You don't have to recompile or redeploy the OS. You don't have to recompile or redeploy the OS services like networking, file systems, graphics. And of course, the applications that you've built on top, most likely they won't need changes. Now, of course, if the hardware that you're using comes with new or upgraded peripherals that you want to use from an application standpoint, you would have to change your code. So if you're using an SoC or a chip that historically didn't have Wi-Fi support, but now you've upgraded to use a chip that has Wi-Fi support, and you have Wi-Fi drivers now available with the OS. What ends up happening is that if you want to use Wi-Fi, you have to make changes in your code to be able to use Wi-Fi effectively. But that's, at the end of the day, that just comes with migrating and changing the hardware. But really, the architecture that we provide allows customers to not be tied to a specific hardware vendor, which is something that our customers love about us. Now, the QNX OS is POSIX compliant. It's a POSIX-based OS, similar to all the open source OSs out there, like Linux, FreeBSD. All of them are POSIX-based and support POSIX, whether it's POSIX SE 54 or 52. I think it's 54 that's primarily being used for OSs. So what you see is that the APIs that you would see in other OSs like Linux, you would see the same APIs available on QNX. So for example, if you're using Linux and let's say in your commands you have POSIX spawn, right? As an example, right? You're using it to spawn processes or threads, or like whether it's pthread or other aspects. That functionality and that POSIX API is supported on QNX, which means that if you're using POSIX spawn on Linux, you don't have to change your code to use it on QNX. The behavior is the exact same. Why? Because the OS implements the API for POSIX spawn on Linux and on QNX the exact same way, because we're aligned to the POSIX standard. And that means that you won't see changes in behavior. The API remains the same, which means that you're API compliant and ABI compliant. So from an application standpoint or a binary standpoint, you don't have to make changes. Now, of course, we have support for a lot of the Unix-based utilities that are available in Linux, FreeBSD, and other functionalities to make the migration a lot easier. So, for example, you can see the address sanitizer, the leak sanitizer, libunwine, ubsan, and other utilities available on QNX, which are also available on Linux. So that way, if you're used to these commands and those utilities, using them on QNX is there. And when you're compiling, we use standard tools. So our compiler is primarily GCC based, which means that if you're using GCC on Linux, so as like let's say for example you're using Linux 5.x and you're using GCC 5 or sorry, not GCC 5 is very old. If you're using GCC 8 or GCC 9 or 10 and you're migrating to QNX and you're using GCC as well with QNX, the compiler with all the options that you've historically used is the same. So it makes the migration and using the compiler a lot easier. And of course, we are using Eclipse-based IDEs, which again, if you historically used Eclipse-based IDEs, using them on QNX is pretty much the exact same. And the other benefit of our OS and the way we've designed it is that the source code and the binaries that you're developing are interchangeable between what we call the non-safety certified OS and then the safety certified OS. You don't have to change anything. So that's very important, because what we see in the market is that we have customers who start the project using the non-safety certified OS, but 6 months in, they realize safety certification is now a requirement, so they need the safety certified OS. So they come to us and say, should we be worried? Like, is it going to be extra work for us to migrate? And the answer is always no. It's ABI and API compatible between both products, so you don't have to do anything. Now, of course, we do have, if you're having any struggles with migrating from Linux to QNX, because Linux, even though it's POSIX compliant, I'm using Linux as an example, but if you're using Linux for FreeBSD, even though it's POSIX compliant, but there are APIs that are specific to Linux. It's not POSIX-based, but it's Linux-based APIs. So we have a porting service available, so we can work with the customers to ensure that when they're migrating those APIs over to QNX, they're using the QNX equivalent. So when we talk about open source standards, we have a lot of standards that we support with QNX. So whether we're talking about different programming languages from C++, to Rust, to Perl, to Java, to Python, to C. All of that is available with QNX. And of course, if you're looking at middleware components like the Robot OS ROS v2, vSUMIP, CAN support, OpenPAM, TensorFlow for artificial intelligence, all of that is available. Like we have functionalities available with QNX, so you can be able to use those components a lot easier. So when we talk about now QNX solutions for software-defined vehicles, what I want to try to start with is where is the market going? Software-defined systems is fast becoming a reality, and it started maybe with automotive being at the forefront, right, with autonomous drive, but you're starting to see industrial systems, rail, medical devices being very, 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 very software defined, and they're using software a lot more, and that means that they're using SoCs, so they're going from microcontrollers, so MCUs, to microprocessors, MPUs, and MPUs are becoming very powerful, and by systems becoming more software defined, and now you're using SoCs, it means that you're gonna have functionalities on the system that is called mixed criticality. Mixed criticality means that you will have components that is running on the OS that is safety critical, and then components that is running on the OS that's not safety critical. So for example, some libraries that you ported over from open source that you just need for specific functionalities, having the ability to manage both safety and non-safety critical software on the same OS is key. And that means that you need functionality safety certification mechanisms for what is called temporal and spatial isolation in the OS or in the hypervisor. I spoke about hardware. The next generation hardware that's coming for embedded systems is very powerful. Historically, embedded systems used to be a quad core, maybe dual core. Sometimes it was a single core system. Now, an 8-core SoC is becoming the norm. There are actually SoCs, like chips out there that are 12, 16, 32 cores, and that's fast becoming a reality, which means that if you have more CPU, more memory, you can do more software on the system. So if, let's say, you're driving an OEM was using 5 SoCs, each SoC was quad core, so 4 cores on each SoC, and each SoC was using and and it was implementing specific functionalities from a software standpoint. If the next project is now you're using a 16-core SoC, you won't have 5 16-core SoCs. No, what will happen is that you're gonna consolidate some of the SoCs and the software that you were using, and just maybe use 2 16-core SoCs, maybe sometimes 1, and just consolidate everything and get rid of the other SoCs that you were using, because you now have a very powerful SoC. And this means that safety and security requirements are becoming key. So because now consolidation is happening, autonomous behavior, fully autonomous is really the goal, with artificial intelligence being at the heart of it. What you will see is that governments and regulators in Europe, in Asia Pacific, Middle East, and in North America, safety and security requirements and regulation is going to come into play to make sure that if you have something that's fully autonomous, you don't want things to misbehave. So if we look at automotive, the end goal and the desire for car makers is really to have one display, one dashboard that has everything you need. And that dashboard is running on one chip, one very powerful chip, and you have multiple virtual machines, obviously running a hypervisor, and each virtual machine is doing a specific functionality. And what ends up happening is that these virtual machines are separated, but you have one display. So if you look at this use case, you have on one display, you have infotainment, active safety, and you have advanced navigation, vehicle control, and you have potentially curated content that you might need. And of course, in the future, if there is no steering wheel, you could have custom services that you would want in your display. And doing all of that on one SoC comes with a lot of complexity from a software standpoint. So if we look at software-defined vehicles, what you're seeing is what sometimes is called zonal architecture, high-performance compute, depending on which customer or which OEM is using it. What you're seeing is that the engine control units in a car, they're being consolidated into very powerful SoCs that's really running more and more software functionalities. And this is an example of really what the end goal is for automakers. They want to consolidate as many ECUs into a very, very, very small subset of ECUs. And in each ECU, you want to have very specific and tailored functionality, of course, running on an SoC. Now, if you look at industrial, you probably know industrial 1.0, 2.0, 3.0, 4.0. You've heard of them before. And of course, industrial 4.0 or industry 4.0 is associated with SCADA, connected factories, and a bit of autonomous and automated functionalities in a factory floor. But industry 5.0 is coming. And industry 5.0 with certain companies is already there. And industry 5.0 really is whether we're talking about humanoids as part of a factory floor or using artificial intelligence and machine learning on robotic arms or as part of the manufacturing floor with cybersecurity integrated to it and functional safety. Because industry 5.0 is all about how to ensure that in a factory floor or an industrial system in general, it doesn't have to be a factory floor, you can have people and equipment working together. And I'm not talking like in industry 4.0, you have people managing remotely the systems that are running on the factory floor. No, I'm talking about being able to go to a factory floor and work collaboratively with a robot. Give it instructions and be able to work collaboratively on the factory floor together. That's the end goal with industry 5.0. If we look at medical, we see that the medical industry is innovating very fast to do more with less. So they want to use a lot of automation. They want to use AI and ML to help with, for example, X-ray and MRI analysis to do initial diagnosis on the MRI or X-ray images that come, or ultrasound as well. You want to use telehealth for a lot of the initial diagnosis that you would see. And of course, you want to be able to be fully digital from day one. And you want to have, of course, automated systems in place to be able to help with surgical procedures. So we see in some cases, of course, like I use the laser eye surgery as an example, but you're starting to see more and more robots and robotic arms being used in the surgical rooms, especially in Europe, North America, and certain APAC countries. They're starting to use robotic arms a lot more to help a surgeon in the surgical room. And this is what you're seeing with healthcare. This is where all the innovation is going to come in the next 5 to 10 years. And when we look at, lastly, rail, is fast becoming more digitized, whether it's because of urbanization, population growth, or other environmental concerns because of climate change. Rail is very green when it comes to addressing the climate change concerns, but you're seeing a lot of rail services becoming more digitized, automated, and you have fully autonomous operation in certain countries like Japan or in China or other North American or European countries where you have a train with no train conductor. The train goes knowing exactly how to go with all the sensors on board. So if there is something that goes on the train track, it can stop instantly, and it goes through all the stops with no issues. And you're starting to see it in those countries where you have fully autonomous trains. So when we talk about what QNX has to offer, we talked about the software development platform. What I want to also highlight is that we also have the hypervisor, the QNX hypervisor. We have frameworks and add-ons. We have cloud enablement with QNX Accelerate. And of course, BlackBerry IVY to complement all of that. And really, we are providing solutions for the intelligent edge. And the objective of the software that we develop is to ensure that whether you're using a 4-core system or a 16 or 32-core system, where you're doing consolidation, you can use a very reliable, safe, and secure OS hypervisor framework from day one. That means that safety certifications and security certifications are key. So safety certification to different standards: ISO 26262, IEC 61508, IEC 62304, EN 50128, and 50657. Those are key, and having the highest SIL, what's called SIL is safety integrity level. Having the highest safety integrity level is key. So for ISO 26262, it's ASIL D, and for EN 50128, it's SIL 4. That's just an example. And for security, you have to have the tooling in the OS and the hypervisor to be very secure. You have to have crypto algorithms, PKI, certificate management, code signing, incidents response, and of course certification, whether we're talking about to the regulations for WP29 that came out from Europe, or ISO 21434, or common criteria for 15408. So all of that is available with QNX. And if we look at our partner ecosystem, what you see is that QNX has a vast portfolio of partners out there. Some of the names here are not going to surprise people, and you see some of the big names like the Amazon, Microsoft, Epic Games, Apple, ARM, and others on this list. I mentioned about how the QNX SDP is the foundation. Really what you see is that the QNX SDP is the core, the hypervisor is an extension of it, and the QNX OS for safety and the QNX hypervisor for safety are built on top of both. That means that the source and binaries that you develop on SDP are the same, and they don't have to change with other components. The tooling that you would use, like Momentex, the CI/CD build servers, the APIs, the documentation, all of that is shared, and all the updates that you see are shared. So security updates, safety updates, new features, roadmap updates, all of that is shared amongst all products. And on top of that, we have a lot of other components that we build and we release: multimedia, encryption for safety, file system for safety, communications for safety, software-defined audio, BlackBerry Ivy. All of that is built on top of our core products. So if you want middleware solutions to complement the foundation of your embedded system, of the embedded OS or embedded hypervisor, all of them are available for you as well with QNX. I mentioned safety certification. Our OS and hypervisor are safety certified by an external auditor, so we actually don't self-certify. Some companies out there actually self-certify, which means that internally they have someone who assesses and gives the certificate. We don't do that. We go to an external auditor to be completely unbiased. We use one of the lead auditors in the market, to Rhineland, to get the OS assessed and safety certified using that specialist, and they gave us the certificate. We have a very strong safety culture because when we started safety certification, we started it in 2010. So it's now been over 14 years of us delivering safety critical and safety certified products, which means that the safety culture is embedded in our processes, in the way we train, in the way we start. So when I first started at QNX 4.5 years ago, the amount of training we had to do on safety and the quality standards that we have and the quality processes that we have in QNX from a safety standpoint is very rigorous, to ensure that when you're working from A to Z, from the moment you start developing an idea for a product to the moment that product goes out the door, the safety culture is taken into play. And we have a success rate of 100% in achieving safety certifications because of the safety culture that we have. I'm going to switch over to Ahmed to talk about the hypervisor.
Yeah, I think it's a quite important topic after this great topics you just spoke about. Why? With this new zonal architecture and this big domain computer and domain controllers or high performance computers, then comes the role of this, what we call hypervisors. I think the hypervisors is well known in the desktop environment and the cloud environment, Most of people may know it. And also now in the embedded environment, just due to this powerful hardware we have today. So what is actually a hypervisor? And hypervisor is actually known also as a virtual machines monitoring. It just imagine like you have a big computer, and this big computer has a lot of resources, and you need to use it efficiently. So you try to divide this common hardware into pieces and run on top of that set of virtual machines. Each virtual machine will actually see this physical hardware as its own hardware, like it's really running on the same hardware, like it's running on it natively. And this actually gives us good separation between these different virtual machines, full utilization, the efficiency of the using these powerful hardwares we are speaking about now, which is becoming trending now in the automotive industry and other industries. But automotive is now, I would say, the leader in most of these discussions now. So the hypervisor in general, we have two types, or the well-known two types of hypervisor. One is what we call full hardware virtualization. So you can virtualize everything on the hardware, and all the different virtual machines can access all the different peripherals existing on the hardware. Very famous, I would say, examples. So cloud, for example. Today, if you run something on the cloud, that's full hardware virtualization, because you can just connect to a certain cloud provider, for example, and use existing hardware available on the cloud without really knowing where is it running. Your application is just doing the same job, but how is it actually communicating with the hardware? You are fully abstracted from knowing that. And the other approach, which is type 1, what you call the bare metal, that you have exclusive access of the resources from a specific virtual machine or from a specific guest running on top of the hypervisor. And here we call a separation of kernels. So if you go more to the type 1, then you have a complete separation between two kernels running on top of the same hardware. And if we go more to the left side, then we are somehow fully virtualized. What QNX actually doing in that? So QNX is something in between. So we really claim ourselves is a hypervisor which can be scaled in both directions. You can go up to type 1, which means work fully with hardware isolation, complete separate kernels, fully and exclusive access of a certain device drivers and the peripherals for a certain guest. And we can also go extreme to the left, similar to the full hardware virtualization existing solutions, to virtualize all the different peripherals available on a certain hardware and share them between the different virtual machines running on top. And we can maybe jump to the next slide, which we speak more about our hypervisor capabilities. So what are the value actually of using a hypervisor in any kind of system? That's just like a generic statement. As I just mentioned, let's just imagine today that you have a bunch of applications, bunch of different systems running separately in your car. For example, one system is just doing like infotainment functionalities. One system is doing the instrument cluster functionalities, ADAS functionalities, and the existing architecture in most of our vehicles today. You have separate ECUs. Each system is just running on one of these ECUs and providing the functionality out of it. With this new trend coming in the automotive industry, with this zonal architecture, high performance computer, having a lot of connectivity functionality, have a lot of power, had a lot of cores, how we can make use of this big computer in a way to deploy all these different systems on the same hardware. And this is what exactly the role of the hypervisor started to play a major role now in this transition with our architecture, in the zonal architecture on these domain controller systems. It's even used with these particular systems individually for other purposes. We can speak about that. But now even the major role has become bigger and bigger. And most of our customers today is asking every day about, how we can move to the hypervisor-based approach. We're getting bigger SoCs, and we need to commonalize and integrate a lot of things together. With QNX hypervisor, the good thing that it's not really like a complete restructure of new concepts. It's just an extension to the proven operating system. So we still have the operating system as a microkernel running in the heart of it, and we have an extension to enable the virtualization, sorry, to support the hypervisor concept somehow. With the hypervisor, we reuse the same concepts already existing within the operating system: security, performance, real-time, reliability. All of these concepts which have been designed with our trusted QNX operating system and the microkernel are leveraged also to be used within the hypervisor host. And as Louay mentioned, our solutions, either the QNX operating system or the hypervisor, both are safety, pre-certified to different standards in different industries. So for automotive, it's ISO 26262 up to ASIL-D. For the industry, it's IEC 61508, and for the medical, it's 62304 up to Class C. And that's also pre-certified product, which you can integrate and use with all the different benefits which I just spoke about. And again, we maintain the same concepts which we already spoke about with the microkernel architecture. So it's still a modular design, enables you to configure what you need for each virtual machine. What are the devices which each virtual machine would like to access exclusively? Which devices you would need to share between different virtual machines running on top of the hypervisor. And that's why it gives you the flexibility that you have virtual machines running on top of your hypervisor, and you select, okay, I need this set of drivers to be exclusively used by virtual machine number one, having the guest number one, and exclusively accessed by these guests. And then the other guests will not be accessing the same peripherals, and you totally secured and isolated these peripherals for this specific guest access. And at the same time, you can select sharing specific devices and all the management of the sharing between these devices following specific standards like VirtIO. This is targeting the visualization. I think most of you may know about the VirtIO. This is like a virtual device driver. It's a standard enabling that the different guests had an operating system and hardware independent device driver, and they can support it. And then later with the underlying host or the hypervisor host, they can communicate with it. And then this is communicating with the back-end driver, which is really the hardware. All the management of this sharing is also going through the hypervisor. And this is also something you can select and scale using the QNX hypervisor. And at the end, maybe if you go back to the previous slide, Louay, just to speak about the last thing. So we are not just speaking about the device drivers, but now we are also discussing about virtualizing the full featured environment existing within QNX. So when I was speaking about which products we offer on top of the kernel itself, we have graphics stack, audio stack, different things. And now we are even discussing like fully featured virtualization of these stacks to be used by the different guests running on top. And that's what I wanted to just give you, like what is the value coming of using the QNX hypervisor. If we go to the next slide, I'm now a designer. I'm just thinking, okay, what would be the best approach while I'm now moving my system from the traditional way of designing my system to a hypervisor devices or a hypervisor-based design. What exactly would be the best approach? Yeah, I think there is two approaches. One approach which would be, maybe if you go to the first slide or the next slide, if I think about it, I have my own virtual machine. I need to speak to certain drivers. I need to have a specific peripherals which I access exclusively. One approach is that you have what we call domain zero or servicing operating system. It's another virtual machine, and it has exclusive management of a certain set of drivers. And what you do in this case, you have another operating system running in another virtual machine, and all accesses from your guest virtual drivers has to communicate to this device driver integrated on the servicing operating system. And this servicing operating system, or what we call service operating system, will take care of communicating to the hardware. That's one approach. So I need to build another virtual machine parallel to the one I would like actually to use, just to service my requests from the hardware. That's one approach. The second approach would be, okay, what about leveraging the hypervisor itself? Because now we spoke about what QNX did, for example. It's already extending the QNX kernel with the virtualization capabilities to provide the hypervisor functionality. So we can do that directly on the hypervisor host without having a new virtual machine just to serve my requests from my guest. But you can do that directly within the hypervisor because there is already a microkernel inside it. And in this case, you can easily, with your virtual machine, just integrate it on top of the QNX hypervisor. Each virtual machine is just dealt with or seen as a process running on top of your hypervisor. And this process is somehow has the possibility via virtual devices to communicate to the host and get the shared devices working with the underlying hardware. And at the same time, because as I just mentioned, we are really scaled between these two approaches, type 1, type 2 of hypervisors. You have also the option to have a pass-through access for selective devices from your virtual machines directly. So that's another approach. So in this case, I didn't really want to build just a servicing virtual machine to coordinate the drivers and the hardware. But instead, I just use the hypervisor host itself to do this job for me. These are two design approaches. Which one is the best for me? That's somehow a design decision. But based on the benefits you can see from each approach, if we go to the next slide, we try to sum up our thoughts about that. With the first approach, as Louay mentioned, with the spatial separation isolation, there is a pros here. If you have this service operating system in a virtual machine, that it has its own protected RAM, but the drivers not isolated within this operating system kernel because it's actually within this virtual machine. And now you have to go through it every time you need to access this particular device. But if you do the same with this microkernel architecture-based hypervisor, and you just keep everything running on the host, the drivers are actually isolated because we spoke in the beginning that the drivers themselves are processes running on top of the microkernel, and they are already isolated, and you can get that for free, let's say. Temporal separation timelines. Also, there is pros and cons with every approach. With the first approach, you can use different service operating scheduler as needed. So within that, you can just manage whatever you need. But for the same time, you will have a latency introduced because you always have to go through this servicing operating system. While with the hypervisor host concept, you don't need to do that because scheduling of service operating system is not needed. You just have your own virtual machine, and you just need to know what are the interactions required between your virtual machine and the host, and that's it. So this is sometimes maybe, how's it called? Costly, let's say. So it's not also free of charge that you just have this communication directly, but it's just that you know what exactly need to have from communication and interaction between the virtual machine and the host. So the corruption of the data, when you transfer the data between the guest and the different service operating system, with the first approach, it's also good, that's why we highlighted that, because you can implement different data validation mechanisms between the virtual machine you need and this servicing operating system. But at the same time, that's also possible with the other approach. For failure handling, I would say there is no pros, because if the service operating system fails, it means that a complete failure of the device. So you cannot access it from any virtual machine. But with the operating system in the hypervisor host, you can actually have a local design safe state. And if a virtual machine is corrupted or it's not running anymore, it's not affecting the others. And the code complexity, that's also one other comparison. So if you have this servicing operating system, you really have a lot of interactions over many millions of code. But with QNX, it's just lower than 1 million lines of code. So there is really no cons in this approach with the failure handling. Driver support, I think we spoke about that many times. So with the first approach, if we spoke about like Linux, for example, each service operating system driver, if we talk about Linux, again, as an example, can be adapted for virtualization. So it gives you a possibility that with this servicing operating system lying in a separate virtual machine, you can always add new drivers which support the virtualizations there. The drivers is always up to date. There is community behind that. But who is updating the drivers? That's always a question, because it's a community based. So you don't really guarantee the quality all the time. You don't guarantee specific constraints for this driver. You need to understand what have been implemented and so on. With QNX, it's different because it's always maintained by QNX team. It follows specific quality standards, and there is definitely cons here because we need all the time within QNX to keep our drivers updated with the latest driver versions actually being available in the market. So these are like the decision metrics which you can think about. Okay, then let's just look at what the market has today. That's just an example coming back from an ADAS background. Today you have, I would say, this ADAS ECU. It has a specific custom SoC running. It may be ARM processor, it may be x86. You have a bunch of basic software drivers and bunch of services available on any kind of platform, just using QNX as of now. We discussed already about different products and different solutions when I was speaking about that. So you have a lot of safety monitoring, safe storage, power management, security policies being checked, the BKI, certified crypto. There is many services available. You can run on top, for example, adaptive AutoSAR environment. And on top of that, you have different applications or different safety applications running on top. This is actually the solution most of you maybe work with today. At the same time, there is additional part of this product, which is really the real-time cores, hosting classic AutoSAR, whatever, but just focusing on the performance cores. That's somehow the traditional architecture today that most of us is just dealing with. And here there is no hypervisor. Now I'm thinking about the move to this zonal architecture with the big high-performance computers, how it would look like. I still need the same application, reuse them as they were used in the previous architecture, but at the same time start to integrate another systems, another applications were previously running on another ECUs within my car. And now I will use this hypervisor-based architecture. And in this setup, I just reused the same exact setup because I was previously running on QNX microkernel. And now I will add the extension for the microkernel to have the hypervisor functionality. I will have new virtual machines. One virtual machine is hosting QNX, Linux, Android, based on whatsoever system you would like to integrate on top of the hypervisor. Let's take an example, the instrument cluster or the infotainment for the information and entertainment, communication gateway. You can integrate all of these different systems in specific virtual machines and run them on top of the hypervisor. Each one of them will be seeing that it's actually running on the same hardware as it was running previously. Each one of them would be like a process running on top of QNX. It has its own configuration. You need to configure all the devices it needs to access and so on. So there is some configuration needed for each virtual machine. What has to be like a pass-through device directly dealing with the hardware, what will be virtualized, shared with the other devices. But this gives you the flexibility that all these systems can co-locate together on the same hardware, giving you the flexibility to scale and efficiently use your hardware. And this is now the trending architecture which most of the vehicle manufacturers are moving into. And at the same time, it also had the possibility to be connected to the cloud. And with this different solution, just I spoke about, they fit together pretty well in these new concepts coming in the vehicle domains currently. One more example, which also gives you like the freedom to design your applications. With this concept I just spoke about, that you have something running on the hypervisor host and something running on the virtual machine, you have easy and very flexible way to select what has to start first. Because normally when you start to boot your system, the hypervisor host start, and later the virtual machines start to run one by one or even altogether, just for example now. And you can keep this, what we call mission critical control applications, running directly on the host. So their availability will be much quicker compared to other systems which may come later. And this gives you the freedom while you are designing your system. That now, for example, I have touch active, I have the rear view camera, I have different like media playback. You can select set of applications to make their availability running quicker compared to the other ones running on top of the virtual machine. And at the same time, later when the virtual machine is ready, like the Android Auto, for example, you can start to get the different Android virtual displays, and the graphics composition is actually done inside the QNX host based on the graphics stack integrated within the host. So you can just have early information available on your screen. And then later, when the Android Auto is available with all other functionalities coming from the infotainment system, you can start to integrate all of them together and start to have all the functions running. But it gives you the flexibility because you had something running on the host to get them earlier than, or with a specific time frame, quicker than the other functionalities you would like to have later on somehow with this approach. Yeah, that somehow gives you the basic understanding of the hypervisor, what the benefits it may give to you. I'm not sure if you would like to add something more, Louay, about that.
No, you covered it very well, Ahmed.
Okay, great. I think that's what we wanted to speak about today. I think we now would like to wrap up. Maybe I go back to Louay just to do the wrap up.
Okay, sounds good. Thanks, Ahmed. Okay, so last thing I want to bring up is resources for you. So I will open up the links. Obviously, you can't see the links here, but I have them here, and I will share them. I will share the slides with Embedded Meetup offline. But I want to highlight that there is a bunch of material available for you online. Of course, we have our latest and greatest version 8 of the OS, which is tailor-made for high-performance compute. Really, the way we've designed that OS was with the idea that we want the kernel to be extremely fast to offset the context switch that you see with the microkernel architecture, and we have achieved it. The other aspects here is you can access the product brief of the latest and greatest OS. You can request a 30-day eval, so you can get access to an evaluation license straight away. You can go and read white papers, and of course you can apply if you're in a university for academic licenses. One thing I want to say before I open up some of these links so you see where they are is we have a new program that has started. We made the announcement in January. It's called QNX Everywhere. The premise of QNX Everywhere is to make QNX available for the open source community very easily, very quickly, which means that there will be more functionalities for you to be able to access QNX a lot quicker and a lot easier for longer periods of time, with a lot more functionalities and open source ports that you would like to see. So I would advise to follow QNX on LinkedIn or on Twitter, on X or Facebook for the latest news, because once we start making the announcements, there will be instructions on how to get access to the QNX Everywhere program, where you can go and access all the new functionalities that we're making available for the open source community. So I will exit the slide and then open up some of the links so you can see. So I'll open up this page. What you see here is the product brief for the OS. This goes through some of the components and some of the functionalities that are available with it, and of course some of the features. To get there, you go exactly QNX.com, and under products here you see SDP 8 or 7.1. So if you come to SDP 8 here, you see this is the web page, and at the bottom of the web page, if I remember correctly, there should be the product brief. So the product brief is here as at the bottom of the web page, and then of course here is the steps to get access to the 30-day license. So you go in, you get started, you create a MyQNX account, you request early access, you request eval, and you get an evaluation license for 30 days straight away. So I just wanted to take you through it here so you know that this is really QNX.com is the location, and you can go in and access the evaluation licenses. And of course, for education, this is the link. So it's blackberry.qnx.com /en/company/QNX in education. Obviously, because this is on YouTube, someone can just pause and get the URL. But really, again, here, if you're working in a university or in high school, you can go here and contact us for applying for an academic license. If you're running into any issues with getting access to SDP 8 evaluation licenses or the educational licenses, please reach out to QNX support, and we will be able to help you out. At the end of the day, we want QNX to be available for everyone as quickly as possible, so you can be able to use it and play around with it and really enjoy our products that we deliver. There are other marketing collateral as well that we have, white papers and blogs that are available. I'll open up this white paper so you can see again where it is. So again, this is the location for it. And what you see here is just a white paper. You can go and fill your name, submit it, and you'll get access to it. It just talks about our view on the robotic potential. Anything else that I should go through as the last thing? I don't think so. Really, QNX.com is your best friend. If you go there and you're able to navigate, you'll be able to see all the necessary links about our products, evaluation licenses, educational program, and other things as well that you can learn about QNX. Don't forget to follow us on LinkedIn for the latest and greatest announcements, because we have this year in 2024 big product roadmap and big announcements coming. So please keep an eye out, because a lot of these announcements are going to provide a lot of relief with regards to accessing QNX in the open source community. So keep an eye out for all of these announcements. And I think the last slide is just to say thank you for today and for Embedded Meetup for hosting us. Ahmed and I really appreciate it. And I think it's time now for questions. So maybe I'll stop sharing my slides unless someone tells me not to do so.
Thank you very much, Louay and Ahmed. Again, thank you for enriching this maybe community with this hot topic, and we sincerely appreciate your presence here and all the highlights and all the content you shared. Yes, if your time allows, we would like to share some of the remarks, questions provided here in the YouTube chat. Does it?
Sorry?
I was asking if your time allows to share the remarks and the questions shared on the YouTube chat.
Yeah, should be fine.
Yeah.
Okay.
Just your voice is a bit low. Your voice is a bit low for us, just to highlight that.
Okay. Okay. Is it okay now?
Yeah, better.
Okay. Thank you. Okay. Okay. So the first one is from Ahmed Mustafa. He's asking how could he start with using QNX if there is maybe special license? I think this was tackled already.
Yeah.
Yeah, so I think we tackled it. I went through the web page and I showed how to access the evaluation license. So Ahmed, I hope that you can try it out.
Okay, thank you. Another question from Muhammad Abdurrahman. He's asking the BSP, what does it contain if the device driver is near the space? And when what is run in BSP space?
Yeah, okay,
Not sure
but
if- yeah.
I think I'm not sure if he phrased the question correctly or not, but as I just mentioned, the BSP is actually set of drivers. There is also a pretty good documentation available on the QNX. We already have a public documentation describe actually what does it mean BSP, but BSP is not, it does not have its own space. So it's either within the kernel space or within the user space. And the difference between the monolithic and the microkernel, as I just described, and also repeated by Louay, that most of the device drivers are actually having their own processes and running outside the kernel space. They are running in the user space. So that's somehow the big difference. So I hope I answered.
And to add to Ahmed's point, just so everyone is aware, maybe we didn't put it as a useful documentation, but if you Google SDP user guide, we have public user documentation that goes through our architecture in detail, the commands, what's in the BSP. So if you go there and you just search for, I'll use this as an example. POSIX spawn QNX or pthread create QNX 7.1 or 8, you will instantly get access to the documentation because it's public. And from there, you will see in our documentation webpage, going from the architecture all the way down to all the commands and how they work on QNX and what's in the BSPs all there. So if you want to know more information, that like more technical information, that's the best way to start doing it.
Okay, thank you. And then we have here a discussion between Alaa Mahran and Abdullah Rashid. Alaa is referring to QNX as Linux stripped out of functionality, but then Abdullah Rashid, yeah, he highlighted that it's a real-time operating system, not just Linux.
Yes, so let me add to it as well. Our kernel we built it. It's our proprietary code. We have a big kernel team we have a joke at QNX saying if your IQs are less than 200, you're not going to make it to the kernel team. But really what you see here is our kernel is proprietary. Yes, from a kernel standpoint, the behavior that you know from general OS kernels is the same. But if the assumption here is that we took Linux and we stripped out the functionalities and we took the kernel of Linux and we stripped out all the device drivers, networking file system. No, we didn't do that. We built it from scratch ourselves. We built our kernel ourselves from scratch from the 1980s. That has been our motto. Now, obviously, some of the OS services that we have are based on open source. Like, for example, we have the Squash file system that's ported from Linux to help with the migration from Linux. Our networking stack components of it are based on FreeBSD, but our core, the microkernel, we built it ourselves.
Okay, thank you very much. And then we have a question regarding the adaptive AutoSOAR services.
So the adaptive AutoSOAR, from an OS standpoint, the requirements are very simple. We are adaptive AutoSOAR compliant from an OS standpoint. Really, with regards to GPU-related services, because of our architecture, that sits in the BSP, like that, because the GPU drivers are part of the board support package. If we're delivering the BSP, then yes, we have to align with what adaptive AutoSOAR wants. But if the BSP is coming from the silicon vendor directly, then what ends up happening is the silicon vendor has to comply with the standard. We have many partners who comply with adaptive AutoSOAR and provide adaptive AutoSOAR solutions like Vector, Electrobit, and others. So, and we're obviously part of the adaptive AutoSOAR consortium. So that's the best answer I can give, because the requirements from an adaptive AutoSOAR and the OS are very straightforward.
Okay, thank you. I think the next one would be a question from Ala Mahran. He's asking if QNX SDV support new Vim. Is this a new Vim related to Vim, the text editor?
I think NeoVim from just a quick Googling is another IDE, or is it a development environment from? I'm just trying to. It's based on Vim. We support Vim, but we don't support NeoVim. No.
Yeah, that's what I wanted to say. Yeah.
Okay, thank you. And a question from Gurdeep Bahmaro. They are asking if the ComStack's QNX is supporting offer easily compliant or compliance.
So we have what we call the communications for safety, which is not a stack. It is a way to mitigate against using the network stack from a safety standpoint. It implements, if you Google the black channel principle in IEC 61508 and ISO 26262, but our network stack, no, is not safety certified to ASIL-D. There are components of the network stack we call LibSocket, which is really the interface to the underlying network stack. So there is work that we're doing right now to make it ASIL-D. But the reality is the entire network stack to certify to ASIL-D is a massive undertaking.
And also questionable sometimes. Do you really need to do it or not? Because certifying everything to ASIL-D is actually a costly thing.
Well, not just that, but if you certify the network stack to ASIL-D, it means all the device drivers that are dependent on the network stack have to be certified to ASIL-D as well.
Yeah, exactly.
Yeah.
So it really depends if you really need to do that or not. That's why we always recommend if someone come and tell us, okay, I need everything to be ASIL-D, we just question why.
Yeah, we need to understand what are you trying to do?
Exactly.
What is the use case?
Yeah.
Okay, thank you. And I think it's not a question, but Prince Adam is maybe providing a remark that in the past he had some issue in the integration between QNX 6.2, and then he found that the bootloader was the root cause.
Yeah, it's not that. I think it's not really a question. I think he's just saying it's not really.
It's a statement.
Yeah, it's just
okay.
a statement.
Okay, then the next question will be related to hypervisor.
It will not.
I'm not sure if I got the question.
Yeah, the hypervisor is actually intended now for these new generations, let's say. With this new zonal architecture, as Louay mentioned, that I also repeated, it will be, for me, it will be a fundamental component really to utilize the different resources available in such big SoCs or HPCs. For the existing systems as of today, yeah, it may be a question mark. Maybe you don't need it. So it depends what are you doing, which design you are using, and what are the complexity you would like to reach.
Yeah, and keep in mind that Android does not run on QNX bare metal. Like Android does not run on the QNX kernel because Android is an OS. It's its own OS based on Linux. So you can't have Linux running on another OS. It has to be somehow virtualized. So if you're consolidating functionalities in a car and you want to have Android and, let's say, for an example, ADAS, right? You want to have the ADAS software running next to Android. The ADAS software is running on QNX and Android is just its own OS. So what ends up happening is that you actually have to use a hypervisor to be able to run both on the same hardware. Now, if you have two separate pieces of hardware where you have a piece of hardware running Android and a piece of hardware running ADAS, you are right. You don't have to get a hypervisor. It's a waste of time. But if you're consolidating functionalities and you're trying to do more and you're using different OSs at the end of the day, really a hypervisor is to be able to run different operating systems. If you're using different operating systems, then yes. Like we even have customers that run Android as in one VM and automotive grade Linux is the second VM. They're still both Linux. but different flavors
and different functions behind them.
Yeah.
Okay, and another question from Ahmed Ismail regarding maybe the idea of abstraction. How the hardware could be changing from a car to car, and also the full package would be dynamic.
I'm not sure if I need to speak about that, but there is also some concepts now being discussed. I will not speak in context of QNX only, but in general, about the containerization also in the automotive industry, which would allow you to do that. So it's just a matter of having a specific hardware with specific capabilities, with a specific performance and memory, for example. And then with this containerization concept being discussed now, you may achieve this. Maybe there is concerns now from safety point of view about the deterministic behavior of these setups. But yeah, generally with these software-defined vehicles, there is many concepts coming from the other industries are currently being discussed, I would say, massively, and even being demonstrated to achieve what you're actually asking for. That's just something, even if the hardware change, things has to work. So they need really to reuse the existing concepts for the mobile communication industry, for example, also within vehicles, that at any time I can go to a specific store, download a specific new functionality on the same hardware just to get it running. And this would be possible, I think, with these new concepts being discussed now with the microservice architecture, the containerization in the automotive industry. But yeah, that's my view on that. So there is definitely hurdles and obstacles to do that, especially with safety. But yeah, that's the way to go. Would you like also to comment on that, Louay?
No, I'm good.
Okay, and the next question is from Karim. He is asking if there is any maybe chance to that the code could be delivered for easier development and debugging process.
So open, I think he means open source for Karim. So part of QNX Everywhere, it's going to be part of the work that we do. We're looking at making potentially some components of QNX open source, and if we don't want to make some of our proprietary code open source like the kernel, then you're going to have the binaries available.
Yeah, but the answer as of today, no, right? So
well, as of today, no, but we've made the public statement that we want to be very open source friendly.
Yes.
And make and let the ecosystem environment and the ecosystem that like the open source ecosystem, like all the people that contribute to open source, to really use QNX the same way they use Linux. Of course, like, there has to be some constraints, right? Because Linux and QNX are different from a commercialization standpoint. But we're getting there.
Yeah.
Okay, thank you. And also another question from Ahmed Ismail about the OEM integration. How an OEM will integrate QNX from different Tier 1 suppliers.
So we work with OEMs and Tier 1s. There is very close relationships with both of them. So whenever a project starts, and Ahmed obviously is managing multiple projects in that sense, and one of probably some of the people on this call are from one of the Tier 1s in Cairo. But the reality is that we work hand in hand. So we have a very close relationship with the Tier 1s, the OEMs, and we work very, very, very closely together. And at the end of the day, the objective for all of us is to ensure that the car goes in production as quickly as possible.
Okay, thank you. Muhammad Nabid is asking how to extend the safety critical applications like ADAS and how real-time QNX features, considering the virtualization overhead.
So this is where Ahmed spoke about if you're running the ADAS features on QNX with our hypervisor, you can run them directly on the host. You don't have to run them in a VM. Like, you don't need the QNX hypervisor and then put a QNX OS as a separate VM. So by having that ability to scale from a type 1 to a type 2, what ends up happening is that you do have that ability to remove the virtualization overhead by running things directly on the host. And that's what we're seeing in the market. Like a lot of our customers are deploying the ADAS functionalities directly on the host and running Android, AGL, and whatever in virtual machines.
Yeah, that's one aspect. The second thing is also what we talked about is even within the virtual machines, maybe for specific drivers, you may have what we call the pass-through access. So they really have exclusive access to these peripherals without any virtualization, even from a virtual machine context. From safety critical, I would say in general, as Louay mentioned, yeah, there is definitely within QNX for this specific kind of product, safety constraints you have to be taken care of. So whenever you integrate your products on top, not to impact the safety certification of the product itself and also your applications, you have to follow this recommendation. And this is also drive or frame what you have to do, what you should not do.
Okay, thank you. And we have a question from Wesley Torres. How long it takes to mission control applications to be started?
It depends. So yeah, you have flexibility, not really to, because with our booting sequence, you have actually the possibility to have like a hierarchical way of put certain pieces and then remain with the others, like put the first important processes first with the drivers required for that. So there is no, I would say, concrete numbers here because there is a lot of factors may impact this calculation. It depends on the hardware itself. It depends on what exactly the mission control applications you are speaking about, which drivers they need. And so I cannot really say like a specific number, but what I meant by this flexibility that you can get them running much earlier compared to something will be coming later with the virtual machine. But it depends on the case and the use case.
Yeah, but what I can add as well, Ahmed, is that from my experience with whether it's OEMs or customers, we have use cases where from startup to an application running, like a safety critical application, in under 1 second. Like it, and our OS obviously because of our architecture can do it easily. Like we can boot up in milliseconds.
Yeah.
Right. So the answer is in a lot of cases it's under 1 second. That's how quickly a lot of customers want certain applications to start on boot up.
Okay, and another question from Ahmed Ismail regarding the debugging of an application.
So obviously you can use our IDE because our IDE comes with memory analysis, kernel tracing, and other functionalities to debug. Without using GDB, it's a tricky one.
Yeah, but what does it mean without using GDB? Do they have any specific hardware debugging techniques which they are using actually?
Well, you don't need target side GDB to do debugging with QNX.
Yeah, on the target we don't
you don't
use
need
GDB.
it, no.
We have another thing, yeah, exactly. But you need the GDB, GDBMI on the host side.
On the host, yeah, in the development environment.
The target, exactly. And for this, there is different methods, and it depends actually what you're doing. So this question maybe, yeah, we can take offline or we can speak about it.
It seems like Ahmed is working directly with QNX.
Yeah, looks like
that question basically tells me that this Ahmed knows QNX inside and out.
Exactly.
Okay, and one more question from Ahmed regarding the having different vision applications and how the QNX is managing the virtualization and GPU access.
Yep. The answer is yes.
Yes.
Okay, thank you. And then one final question from Ben Salim. It's related to the running intensive AI algorithms, and is it possible to be maybe utilized or used for QNX?
So what I can say publicly is that we have AI algorithms right now in the field running QNX specifically for ADAS. And at CES in Las Vegas in January, when I was there, we showed the next generation OS running TensorFlow, which directly on the OS. So to showcase that yes, you can run AI algorithms on our next gen OS. So can QNX run resource-intensive AI algorithms? Yes, but how resource-intensive are we talking here? Because at the end of the day, when you're running in a car, what we see from customers is that the AI algorithms are contained. You don't want something to really absorb all the CPU and memory. You try to restrict it as much as possible because you have other functionalities that is also running.
That's one thing, and I think most of the new SoCs actually came today with a specific accelerators and a specific processing unit for specific AI applications, and they normally would like to offload these specific algorithms to be running on these specific accelerators, not really, not to overload the performance cores with such AI.
Yeah, like the neural processing unit is one example.
Exactly. It's like NLP. Yeah.
Okay. One more question regarding the computation cycle configuration.
So the QNX OS has two options. You can run it ticking, so it's based on the hardware timer. We call it ticking operation, but it's also tickless. So there is an option to run it in tickless mode. So from a timing standpoint and a computation standpoint, the two options are there. You can use hardware timers if you want, or you can run in tickless mode where you're not dependent on hardware timers.
And you will also find some information about that in our official documentation.
Yep.
Okay, thank you. And finally, question from Mohammed Abdurrahman regarding the ongoing trend to use Rust, which is a secure programming language, in building open source operating systems. So I think he's mainly asking, will QNX be affected by this trend?
Do we support Rust or not?
Yeah, we support Rust. So Rust is supported on SDP 7.1, and I'm working on supporting it for 8 right now. So the answer is yes. So from a safety standpoint, our customers haven't come to us and said, we want to use Rust in safety. And I think the reason why that it hasn't really made its way to safety yet is because Rust is still a new programming language, and there is a concept in safety. It's called the proven in use, or you have to do a lot of data modeling and safety modeling to justify and to prove that whatever you're using is safe and secure, because that's what the safety standards dictate. So we see customers using Rust maybe in QM, maybe ASIL-A based systems. There has been talks about using Rust to ASIL-D, but the uplift to get Rust to ASIL-D is a lot because the proven in use argument is not there.
Okay, thank you. And I think it's an extension to Ahmed's Ismail question regarding the debugging. Andrew is asking about the cooldowns.
Yeah, you can use Momentex for that. So as we just discussed, we have our IDE, which you can actually load the core dumps there. There is a possibility to also have, if you really use the same binaries which you build for these core dumps, there is memory and address translation, which you can somehow load with this memory, with this core dump. And if you do everything correctly, then it will be pointed out to them. Sometimes we see some customers are like, he has his own local builds with source code which is not matching the core dump, and things are not working. And yeah, if you do that the right way, you can look at the code and try to see where is exactly the problems happening.
Yeah, what I can say, Andrew, Ahmed, is that a lot of the people and a lot of our customers don't use Momentex to its full potential.
Yeah.
Yeah, and there's a lot of hidden gems and a lot of functionalities in Momentex that when we tell customers about it, they're like, "Oh, we didn't know Momentex supported that." Obviously, with an IDE, because of just its massiveness in terms of tooling, it can sometimes be not easy to figure out how to use it and what functionalities is there. But to add to Ahmed's point, yes, a lot of the questions here are easily supported.
And so, sorry, Louay, again. And again, also with our official documentation, there is a big section talking about the IDE.
Yeah.
And there's a section talking about, core dumps, kernel traces, debugging the performance of a certain product. I think all of that are covered. So if you're working in a certain project with a certain customer, you can also approach us from the services are given to you, and we will support you with that.
Yep.
Okay, then I think this is the last question. And again, at this webinar is approaching its end. Thank you for joining us, and thank you for sharing all these insights and knowledge.
Our pleasure.
Yeah, our pleasure. I think it was quite a good one. We tried to cover as much as we can. Yeah, thanks for hosting us, I would say, as I also mentioned, and looking forward for everyone join this to get the benefit out of it and to start to use QNX if they are not. And if they use QNX, start to dig more into the different things coming and keep an eye on the big announce also happening this year.
Yep. And if you have any issues or any problems that you run into QNX, call Ahmed.
Yeah,
Okay.
our roads will cross some way.
Okay, thank you all, and looking forward to maybe another chance to meet with you. Thank you.
Yeah, thank you.
Have a good day.
Bye.
Bye.
Bye.